9 and welcome to our second lesson today on Introduction to Plate Tectonics. Well done for those of you that completed last week's lesson. I was really quite impressed with the quiz, although I have to say some of you are really slow at actually completing it. By the fourth day of it being up, we barely had a third of you doing it. So let's see whether we can speed that up this time and get a lot more of you completing it a bit quicker. Also trying to get full marks. Some of you, your scores are a little bit low. I'm wondering whether you actually have read the PowerPoint, looked at the video and really made some notes. I have to say, some of the best notes I've seen, I'm going to give a shout out to you, Piper. I thought your notes were really thorough and really brilliant. Like the colour coding, and I think you're doing a really good job. So let's see who can get a shout out for the next week's piece of work. So I've got a bit of an interesting starter for you to do this time. It's a bit of a code. You are going to need to do it because one of the lines of answers is actually needed, in fact all of it may be needed in the quiz that's at the end of the lesson. So look carefully. To give you some clues, if you have a look, what you have to do is, if you see here that you've got the number 8, just trying to draw the number 8 here, okay, and number 8 here represents the letter Y. Every time you see this, that means that there's a change in word. Look carefully though, because over here I just couldn't fit the whole word onto a line. So what you'll see is that this word here actually is 1, 2, 3, 4, 5, 6 letters long. So have a go at doing that and it will tell you a little bit about what the lesson is about. So the main idea of this lesson is about plate tectonics and how many different directions can they move in. So what we're going to learn about today is recall a little bit of the characteristics of the Earth's crust. We're going to illustrate how plates move, and we're going to explain the features created by these plate movements. So I'm going to give you a moment and let's see if you can name any of the world's major plate names. Now you can put this on pause and I would suggest you do it when I finish speaking now, and then when you think you've guessed them all you can continue to hit play and you can name them all and see how many you've got right. So hit pause now. So the first one, the North American plate. Second one, the Eurasian plate. Third one, the Pacific plate. Look carefully because what you'll notice is that this is also the Pacific plate here. The fourth one, the Nazca plate. The fifth one, the South American plate. Sixth is African. Seventh is Indian. Eighth, the Australian. And ninth, Antarctic. Now these are some of the major plates. What I think is interesting is if you look at this one and this one, see if you can have a go at finding out those three as well as that fourth one. Okay, a bit of a challenge there for you, see if you can get their names, but well done if you've got the 9 major ones correct. So I mentioned this phrase, plate tectonics. Now it's something that you may have done if you go back to your work that you learned about in year 7. What hopefully you can remember is when we looked at the structure of the Earth, we also had to think about plate tectonics. So those of you who did quite well last week that remembered that the top layer of the crust is called the lithosphere. And this basically is a massive, what we call irregular shaped slab of rock. And you can see it's irregular. If you just look in the background of this particular slide and all of them, it's got the plates marked on and you can see that they're all very uneven. It's not like a perfect break. And they're composed of continental and oceanic lithosphere or crust. And they can vary in size. I mean, look at the ones that you've just seen and you can see totally that some of them are really huge, sort of thousands of kilometres in size, and some of them are just a few hundred kilometres. We don't know yet whether we've definitely found all of them, but there's loads of quite big ones, and they're all basically pieces of the Earth's crust that have been broken up. Now I want you to watch this video link. It's a few minutes long. There's no words, but basically really have a look at the bottom left hand side. It talks about how many million years ago, or even into billion years ago, MYA, million years ago. And what it does is it gets you to really think about how those plates have moved. And you can see, I think it's quite interesting, from the very, very beginning of when there was hardly any continental crust. And one of the reasons for that is, if you think about it, that once you had oceans, once that water was on the top, in order for there to be continental crust, there had to be oceanic crust first. And over hundreds of millions of years, that built up and up and up, and it had to go all the way building up higher through the depths of the oceans, right up until eventually it became higher than sea level. And so any part of the continents now is above the sea level pretty much. Okay, so have a look at this. In particular, there's two things I want you to really focus on. Is try to jot down roughly the number of million years ago when you start to recognise the current continental shapes, where you start thinking, yeah, I can spot North America, I can spot South America, definitely think there's Africa. Just the shapes, not where they are, because that's the second part. Then have a look to see, when do you think they're getting close to being in the current position that we're now in. What you've got to remember is they are still moving, and we'll talk about that later on. Okay, so hopefully you watched that video clip. This one here I find really quite interesting. Again, it's about 5-6 minutes long, and it talks through, in particular, the fact that to begin with there were people who had views that they knew that the plates must have been moving. And the first person that came up with this concept was back in 1596, and this guy called Abraham Ortelius, I think that's how you pronounce his name, and he was a cartographer, and a cartographer is somebody that studies maps. And he was looking at it, and he began to look at these maps and started to think that some of the continents at one time were most likely all located next to one another. So he had a theory, because that was the hardest part, is that he could say, I think this is what happens, but actually proving it was the difficulty behind it. And he actually just said that he believed that there'd been earthquakes and floods that in particular had separated America, Africa and Europe. And you know, about 90 years later, 80 years later, something like that, somebody else believed that the Atlantic was formed when the land sunk, and that was a guy called Francois Paget in 1666. So we're going back hundreds of years that people began to believe this, but nobody quite actually could say why. There were other theorists that went on throughout the next few hundred years, and then eventually this guy called Alfred Wegener in 1912, he published something called The Origin of the Continents and Oceans, and he basically put forward this idea of continental drift, and he was looking at fossils and rock types and geology and sort of the way in which the land all looked. And what was really interesting is he actually, his job, he wasn't a geologist, he wasn't a geographer, he wasn't a cartographer, he was a meteorologist, somebody that studied weather. But by looking at the weather, he was able to work out as well that different rock types and different vegetation and different animals all inhabited the world at certain periods of time. So in knowing this, he started to think, well, if that animal was there and it could only appear in that climate, and that one was there, it could appear in that climate, and those continents aren't now in that particular climatic conditions, he began to realise that something must have happened, that these plates must have moved. So he came up with this theory, and he called it the continental drift theory, and nobody really believed him. And we were talking 1912, and really for the next sort of 30 to 50 years nobody was really behind it. And the reason I find this so fascinating, I put it on the text here, is I think to my parents who would have gone to school in the 1950s and 60s, I think to my grandmother, all my grandparents, but they went to school sort of the 1930s, and they never would have studied this because nobody could prove it, and they just kept saying, you're wrong, it didn't happen. They didn't have satellites to prove where continents were. They were just relying on probably people who had originally sailed around the world and plotted maps. And we look now, you know, if I said to you, go onto Google Earth, I will guarantee that you will all go and look at your houses. That's the first thing. So if you've no idea what your house looks like, you have to go on and see what your house is. So they had none of this back in 1912, back when my parents and grandparents were at school. Now, what I'm obviously massively impressed with is that the person who finally did this, and I'm obviously being very sexist here, but it was a woman, okay, a lady called Marie Tharp in 1953. She basically went, you know what, I believe that nearly just over 40 years ago, Wegener was right. And then what's really mean is one of her colleagues, Bruce Hazen, he published the work in 1956, basically stealing most of her ideas, but he changed the theory slightly, and he said it was because the world was expanding. He sort of basically said Marie Tharp and Alfred Wegener were all wrong, his theory was right, and he took credit for where he felt he could. And then finally, in 1963, Tharp was proved right, and that meant that also so was Alfred Wegener. And they finally believed that the plates had moved, that these continents had all at one point been in various locations around the world. They'd gone through different climatic zones, they had moved together, they'd moved apart, and also the fact that they were still moving. And the way in which they talked about this, and you can see at the end of the video, they talk about it called divergent or transform and convergent plate boundaries, and we'll talk about that later on in the slides. And there's some newer theories as well called ridge push and slab pull, and these theories as well of how sort of gravity and friction can work together, and a sort of a gravity of pulling down part of the oceanic crust and continental crust being pulled down. Okay, so hopefully you've seen that film. And this here is pretty much what they've ended up concluding. You've probably seen something like this before, especially if you think back to work you did in year 7. So if you look, what you've got is these blue arrows here. They show you the direction in which the plate is moving. So you can see that the Pacific plate is moving away, okay, from the Nazca plate, and that is called divergent, or as we would call it throughout most of this work here, is that anything moving away we would call a constructive plate margin. And the reason it's constructive will become apparent later on, but basically if you're moving away, you're not just going to have a hole. New magma is going to rise up in that crust there and along here. It's going to rise up and cool down and solidify at the bottom of the oceans and create more oceanic crust or lithospheric rock. And as a result, we are moving away, so North America there, us over here, at about the speed in which your fingernails grow, and that's every year we move about that. So it's a few centimetres every single year, so it's a really, really slow process. We've got something called destructive plate margins, and one of the most destructive plate margins, if we look around here in Japan, one of the reasons why Japan has so much tectonic activity. And with destructive plate margins, what we've got happening here is sometimes it's called subduction zones, and we've got the oceanic crust is older and denser and heavier, and it's going underneath the continental crust. So they're moving towards one another, converging, and one is going underneath the other one. Then we've got here, okay, this here is called a collision margin, and basically we've got continental crust here and continental crust here, both moving together. Now they're similar sort of ages and densities, so they just collide, and you get features such as the Himalayan mountains, for example, have formed there. And then not many examples of the conservative margin, but the main one here along there, okay, is what we know as the San Andreas fault, and these are sometimes called transform margins. And basically what's happening here is the plates are moving in the same direction but at different speeds. So you're not creating crush, you're not destroying crust, they're just moving. So you get a huge amount of earthquakes happening there. And I'm sure over the next few weeks you'll probably get a chance, if you really want to watch the film San Andreas. It's absolutely geographically awful. Half the things in there are completely inaccurate. However, I do quite like looking at the rock, so it's got some good things. Okay, a bit of an activity here for you. If you want to print this page out, cut it out and see whether you can position and make your own jigsaw puzzle. If you've brought your books home, you can put it into your books. If not, if you've got a folder, but just to give you an idea of how the plates move, and it's got some of those smaller ones that I mentioned earlier on. Extra challenge, go back to that previous slide, draw on. I would also draw on the boundaries, so where you've glued them together, it will form a perfect rectangle. Remember, you can't have any gaps in it if you put it together. If you've got gaps in it, you've basically eradicated part of the world. So put it all together, and then when you've glued it together, go over the joins in a really bright colour, and that will show what the plate boundaries or plate margins, same thing, are marked on it. But also add the arrows to show whether they're moving towards one another or away from one another, or to transform the conservative plate margin where they're moving sideways. So I mentioned earlier on that these are the main plate boundaries: divergent or constructive, convergent or destructive in their collision or subduction, or transform conservative. So I've got an activity next for you. Again, a bit of cutting out if you've got chance to. I've attached it as a Word document. Apologies now, I have no idea why, but for some bizarre reason the hexagons sort of lose their shape slightly. Now if you look here, you can see that some of them are shaded here. These are the 4 main plate margins, so cut those out, and then what you need to do is you need to put around those hexagons the statements that relate to the right type of plate margin. Now if you don't want to cut them out, or you can't cut them out but you've got access to the Word document, because you can edit it yourself, you can colour code them if you want. So you could maybe make all the constructive plate margins say blue, and then colour code all of the statements that relate to it in blue as well. Okay, using that information now and do some additional research, what I'd like you to do is, again, you can either print this page out, or you can draw it onto a piece of paper, or you could just type it straight onto it or copy it into a Word document. I don't mind which way you do it, but what I really want you to do is basically take each of those plate margins and really identify the key characteristics. So for example, are they oceanic or continental crust? Are they, where do you, right, so what are their densities, their features, again some specific things about those. So again, a bit more about their density, their thickness, whereabouts they can be found would be down here, and their associated hazards, sorry, the features as well. So just going back to that, that's things such as oceanic trenches, fold mountains, volcanoes, etc. So the associated hazards, does it lead to volcanoes or earthquakes? Does it lead to just volcanoes or just earthquakes? Be really careful though, because I've just said there, does it lead to just volcanoes? Excuse me. All of those plate boundaries all will lead to earthquakes, but they might be different severities. Only 2 of them though will lead to volcanoes, and they're different types of volcanoes. So make sure you look really carefully at your notes to tell me whether they're a shield volcano or a composite volcano, and maybe a bit about those volcanoes as well. So that will take you quite a while to do. I've put here a bit of an exam practice question, so have a look here and see whether you can answer those questions. Right, so this final part is a little bit of fun. Okay, I've had a go at Joe Wicks's PE lessons, I have to say. I'm rather unfit, certainly nowhere near as fit as he is. So if you want to have a go at this one, it's not quite as strenuous as Joe Wicks. some of you have done it before. I've definitely heard it coming from Mr. Shipman's classroom, so I know some of you will know this, but let's see if you can have some arm movements. Feel free to take some photographs. You can email them to me if you want, or you can just die of embarrassment and not let anyone else see them. But the idea behind this video is just quickly sort of recap what happens in the direction in which the plates are moving. And lastly, if you could now make sure you've got all your notes, that you've really gone over them, you've really thought about it, and then have a go at the Google Forms quiz, which the link to it has been attached as before onto Teams. So massive well done everybody, keep up the good work, and next week you'll get your new lesson. Take care, bye.